Assalamu alaikum warahmatullahi wabarakatuh. Today we will discuss about a new biasing technique which is known as voltage divider bias. In the last lecture we discussed about fixed biasing, and it is a very simple biasing technique, and we have seen that it is not a good biasing technique and it was not so stable, right? Now today we will discuss another thing which is known as voltage divider biasing. Okay, voltage divider biasing. This is one of the very popular biasing technique. It is one of the very popular biasing technique, and this is a somewhat which is, we can say, it is a good biasing technique. Okay, this is a good one. Okay, it is a good biasing technique. It is a good biasing technique. Now, how we can perform this biasing? As the name says, it is nothing but dividing the voltage, right? It is dividing the voltage from the source. And how to divide the voltage? The voltage division is done by using a voltage divider, that is a potential divider. Okay, by using a potential divider. So this is how we are dividing the voltage. Now we will see how the circuit diagram will be looking like. So we have the transistor. We will be discussing by using an NPN transistor, and the emitter is connected to the ground by using a emitter resistance. The collector will be there. Okay, the collector will be connected to VCC by using a resistance RC. Now at the input side, or at the base side, actually what we are going to do, we are going to divide our VCC. You can connect this VCC like this also. Everything is same. You can connect the VCC like this. So this is VCC. Okay, so this VCC. So instead of showing like this, we can show in another way that I will explain to you. You can see that the voltage is divided by using two resistance, that is the potential divider. So this kind of arrangement is known as the voltage divider bias. You can draw the same thing in a different way also. That means you have the resistance, you have the transistor, you have a resistance RE, and you have the RC also, and you can see that this VCC is positive here, so you can apply here positive VCC. The meaning is that there is a negative, and this negative is going to ground, and you have R1 and you have R2. I hope that this is clear, right? So this kind of arrangement is known as the voltage divider biasing technique. Okay, now we will see different things, characteristics of this voltage divider biasing. So let us draw the voltage divider biasing. So now on, I will be using this circuit diagram. You have an RE, you have an RC, and you have VCC. This is plus VCC, and you should understand that the minus is going to ground. Okay, I will not be showing this minus always, so it is understood. So we have a potential divider R1. Now we have something like now you can see, if you take the voltage division part. Okay, take the voltage division part, you can see that there is a VCC and there is a voltage division, right? This is R2 and this is going into the transistor. You can see this is going into the base. Okay, this is going into the base. Now we can see that if you see from here, if you see from the base, you can see that there is some resistance RE. Okay, there is some resistance RE. You can see there is a resistance RE, and also we have the transistor. So due to the effect of this RE and because of the transistor, you will be the current which is going into the base, we can say that is known as the base current. This is the current which is going into the base, that is known as the base current. The base current may face some resistance. So how to find this resistance? So when you see from this side, okay, when you see from the C into the base will be having some resistance. So the resistance, so if you see from here, you have the transistor and you have RE. So the resistance, and this is RC, the resistance seen at the base, okay, at the base. Okay, how to find the resistance? You know that to find the resistance of any circuit, how to define this? The resistance of a circuit can be obtained by using Ohm's law, right? Suppose you have a circuit with a resistance something like this, some resistance something like some R in or something, some RA for some circuit. If you have a resistance RA, how to find this RA? It is nothing but how much current is going, the current going, it is IA, and suppose the voltage is VA, then RA can be obtained by VA over IA. So you can use the same idea to obtain the resistance which is seen at the base, okay, at this point. And at this point you know that the current which is going into the base is IB. Am I correct? So the current is IB. Now the current is equal to IB, right? The voltage, what is the voltage? The voltage at the base, how much? The voltage at the base is VB. Am I correct? Because this is the base, so at the base the voltage is VB. So the resistance at the base, we can say this is some Rin which is seen at the base, is equal to VB over IB, right? It is nothing but VB over IB. Now we will find how to obtain VB. You know that the voltage at the base, actually you have VBE is 0.7 and the current which is going into the emitter is IE. So the voltage across RE is nothing but IE into RE. So the total voltage that you can see at this end, is nothing but your 0.7 is here and also some voltage here at IERE, right? So it is nothing but 0.7 plus IERE, right? And you know that this is IB, right? IB. But you know as in our previous lecture that we have discussed, that the current IE is approximately, you can see that we have already explained this concept. The current IC is approximately equal to IE. So by using this notion, we can rewrite the above equation as 0.7 plus this, instead of IE we will use IC. Okay, this is for just for simplification, divided by IB. Now you know that this is approximately equal to IC RE over IB. So what is IC over IB? IC over IB, you know this, it is nothing but beta DC. So at the base, the resistance seen at the base, actually this is known as R in base, is nothing but beta DC times RE. It is approximately equal to beta DC times RE. Now we have seen the circuit. I will draw the circuit again. So this is RE and this is RC and VCC. We have something known as R1 and R2. So the resistance you are seeing at the base is nothing but R in base, right, is equal to beta DC times RE. I hope that this is clear, right? Now we will see this potential divider part. We will see now the potential divider part. You have a VCC, you can see here VCC, and you have R1, you have R2. Now the resistance, instead of this transistor I will use the resistance that you are, so this is including both the effect of both, right, the effect of including the effect of both transistor and RE. Okay, so this is nothing but, we can see that this is R in at the base. Now can you tell me what is the total net resistance that you can see here? The net resistance is nothing but R2 parallel R in base, right? And you know that R in base is nothing but beta DC times RE. Now to find VB, we can apply voltage division, right? Voltage division. So the voltage division, by using voltage division, VB is equal to VCC over R1 plus R2, because there are two resistances, one is R1 and another one is R2, but it is not simply R2. The R2 is parallel with R in base, so we can say R2 parallel R in base. Am I correct? So this is the total current. Then we have to multiply this with R2 parallel R in base. So this is how we can obtain VB. Okay, suppose our R2, suppose our R in base, for example, R in base, suppose our R in base is much greater than R2, then R2 parallel R in base, how much it will be? R2 parallel R in base is approximately equal to R2. For example, for example, we suppose R in base is equal to some 10 ohms and 10 kilo ohms, and R2 is equal to some 200 kilo ohms, then you can see here your R2, sorry, suppose you can consider the example like this. Suppose your R in base is something like some 100 kilo ohms and R2 is some 10 kilo ohms. You can see here R in base is much greater than R2. In such a case, you can see it is nothing but 100 kilo parallel with 10 kilo, right? As I told here, this one, okay, 100 kilo parallel with 10 kilo, and this is approximately equal to 10 kilo. You can calculate it. It is approximately equal to 10 kilo. So what is our conclusion? If R2, if R in base is much greater than R2, then R2 parallel R in base is approximately equal to R2. So we will use this idea, and throughout this course we will be considering the cases where R2 is much less than, or R in base is much greater than R2. So in such a situation, in this situation, suppose if we are considering this case, we can obtain VB is equal to VCC divided by R1 plus R2 into R2. Okay, this is simply the voltage division. This is known as the voltage division. So you have an R2, you have an R1, and you have R2, you have a R1 and you have a R2, and RE, and this is RC. So just to simply apply the voltage division to find the voltage which is VB at this point, and because this is the base. Okay, so to find this voltage you can use this formula. So at the input side you can find the VB like this, and at the output side, how to write the Kirchhoff law? You know that at the output side we have the current. This is IC, right? And this current is IE, but it is approximately equal to IC. Okay, so we will not be using IE anymore. Anyway, we will be approximating IE with IC. So please note this point. Now you can see that the current is coming from plus VCC and it is going down to IC, right? So whenever the current enters, you can see that this end will be positive and this will be negative. Now when the current enters, you can see this is positive, this is negative, and the voltage across the collector and the emitter is nothing but VCE. When the current enters here, when the current enters RE, that end become positive and the other end become negative. I hope that this is clear, right? Now we will write the Kirchhoff law. So we have a plus VCC, so you can assume that the minus VCC is ground, right? Now we will start from the ground and we will move to the ground, right? We will start from the ground and we'll end up with the ground. So now when we start from the ground, you can say this is minus, so we can write the Kirchhoff law, the KVL at you can take, this is the loop, it is going round, right? This is the loop 2 and this side you can say whatever you have considered here, that is by using this equation you can say this is loop 1. So by loop 2 you can see that you are starting from the ground, so what your polarity you are seeing is minus, so it is minus VCC. Then you are seeing the polarity here plus, so plus it is IC times RC, and the polarity you are seeing here is plus, so it is plus VCE. The polarity you are seeing here, it is also plus, so plus, instead of IE actually we will be using IC. Okay, so IC into RE. Why we are using? Because for the for uh, for the easiness of the calculation, and you know that IC is approximately equal to IE. So we have finished and we have reached the ground now. We started from the ground and we reached the ground, right? So this is equal to 0. Now we are going to find VCE, right? What is VCE? VCE equal to VCC minus IC into RC plus RE, right? So this is how you can write the Kirchhoff law at the output side. And how to obtain the voltage VC, that we will explain in the next slide. So you know that you have a voltage divider. Okay, I will repeat it. You have a voltage divider biasing circuit RE, and have RC, you have plus VCC, this is R1 and this is R2. Now the main objective, the objective is to obtain IC and VCE, because you know that the transistor characteristics will be drawing like this, right? This is the transistor characteristics. The x-axis is VCE and this is IC, and we have to draw the load line and find the Q point, right? So for finding this, we need to obtain IC, right? So what is the procedure? So the procedure to obtain IC and VCE, it is nothing but, first of all, we will be taking this loop. We will be taking this loop, okay? We will be taking this loop and we will obtain VB first. So what is VB? VB is approximate, it is nothing but VCC over R1 plus R2 into R2, okay? So we will be using this case. So we can use this case when if R2 is much less than, or we can say if R in base is much greater than R2. So anyway, for this for the exam I will be taking care of this, don't worry, okay? I will give you the questions based on this approximation. Anyway, don't worry, okay? Now it is VB is equal to VCC by R1 plus R2 into R2. So once you obtained VB, and you know that the voltage across the base and the emitter, the voltage across the base and the emitter is 0.7. So you can find this voltage. This point is nothing but the emitter, right? This is nothing but the emitter. So the voltage at the emitter, we can say it is VE. So once you obtain VB, you can find that VE is equal to VB minus, you can see this is the voltage VB, this voltage is VB. Now there is a 0.7 here, so so VE is equal to VB minus 0.7. So this is the first formula that for calculating VB. Once you obtain VB, you can use this formula for obtaining VE. Now to obtain IE, you know this is VE, this is the voltage VE, and the current here it is IE. So IE is nothing but VE over RE. So you obtain the IE, but IE is approximately equal to IC. Okay, so you can use this. Now you got IC. So this is the method to obtain the IC. Okay. Now how to obtain VCE? VCE is obtained by writing the Kirchhoff law, so that we have seen already how to obtain uh, VCE. So VCE can be obtained by writing the Kirchhoff law at this side, right? So you are starting from the ground. Actually, there is a ground here. Don't miss this ground. So when you start from here, it is minus VCC. I have already explained this in the previous slide. Then you know that the current is going down, so plus minus, so minus, so you can see the current is going down, and this is plus, so plus IC RC. Since the current is going down, this is plus and at the collector, and minus at the emitter. So the polarity VCE, right? So plus VCE, then the current is going down, this is plus and this is minus. Am I correct? Yes. Now this is VCE, then the current is going down, and this is IE, but it is approximately equal to IC. Plus IC RC, sorry, IC RE is equal to 0, and you can obtain VCE as VCC minus IC into RC plus RE. So this is the method to obtain VCE. So these are all the equations related to voltage divider bias. Okay, now we will see how to draw the load line. Okay, so we have the equation, we have the equation VCE is equal to VCC minus IC into RC plus RE. So let us assume that we can yes, now let us assume that we have x-axis and y-axis, VCE and IC, and this is the transistor characteristics that you know, right? This is the transistor characteristics. Now we want to draw the load line. So load line is actually coming from loop 2 according to this equation, and this equation contains the VCE, that means it is the x-axis, and this IC, that is the y-axis. Now to draw this load line, you have to first find the point on the x-axis. To find the x-intercept, you can say x-intercept, to find x-intercept, put y equal to 0 in the equation. What is y? You know that y is nothing but IC. That means put IC equal to 0. That means VCE is equal to VCC. Next, to find y-intercept, put x is equal to 0. Okay, so what is this x? X means VCE, that is put VCE equal to 0. Now by using this equation, if you put x, VCE is equal to 0, then you will get IC equal to VCC over RC plus RE. Now you got the x-intercept and you got the y-intercept. So this is the x-intercept and this is the y-intercept. So we are going to mark it. The x-intercept may be somewhere here, and this is nothing but VCC, right? You can take this equation. And the y-intercept will be something here. It is nothing but IC sat, we can say, because it's the maximum current. So this is nothing but at saturation. Okay, it's maximum. So IC sat equal to VCC over RC plus RE, right? Now you can draw the line. This is known as the load line. Okay, so this is known as the load line. I hope that this is clear how to draw the load line. Now we will do a problem. So the problem is to obtain the load line. Okay, the problem is to obtain the load line. We have to find the Q point and obtain the load line. Okay, now we will see how to draw the load line. So let us consider a problem. So problem, the question is determine VCE and IC in the stiff voltage divider bias, stiff voltage divider biased transistor circuit of figure below, and it is given that beta DC is equal to 100. Okay, so the question gives a voltage divider biasing circuit. This is having some RE and it is having some RC and VCC. Okay, the VCC is given as 10 volt, RC is given as 1 kilo ohm, this is RE is given as 560 ohm. Okay, and R1 is given as 10 kilo ohm, R2 is given as 5.6 kilo ohm, and this is the circuit. Okay, now we will see this problem in detail. Now first of all, you know that beta is given as, so the answer given that given beta DC is equal to 100, right? So we will calculate R in base first. R in base is nothing but beta DC times RE. Beta DC is 100 times RE is 560. So this is nothing but 56000, or we can say R in base this much ohms, right? So R in base is nothing but 6, that is 56 kilo ohms. Now what is R2? R2 is given as 5.6 kilo ohm. Now you can see the condition I mentioned before. I have mentioned a condition before. You can see this is the condition. If this is satisfying, we can use the formula for VB as VCC over R1 plus R2 into R2, right? Now you can see this condition is meeting because 5.6 or 56 kilo ohm is much greater than 5.6 kilo ohm, and this is R in base and this is R2, or we can say this R in base is approximately or equal to 10 times R2. If you are having a condition at least 10 times, then you can use the formula for VB as VCC over R1 plus R2 into R2. Okay, you can use the exact formula also, but you can use the simplified formula if you are getting a condition at least R in base is equal to 10 times R2. Okay, so we can find VB now. VB is equal to VB is equal to VCC over R1 plus R2 into R2. That is equal to 5.6 kilo ohm divided by, that is equal to VCC is 10 divided by R1 plus R2, and R1 I think it is R1 is 10 and R2 is, so 10 kilo plus 5.6 kilo into R2. How much R2? R2 is 5.6, right? So R2 is also 5.6, is 5.6. So this is equal to 3.59 volt. Now since you got VB, you can find VE as we discussed before. You have used this formula. Now you are going to use this formula, that is VE is equal to VB minus 0.7. So VE is equal to VB minus 0.7 divided by, this formula. So that is equal to how much? It is 3.59 volt minus 0.7, which is equal to 2.89 volt. Now we can find IE, which is approximately equal to IC, as VE over RE. You know VE is 2.89 volt divided by RE is 560 ohms, right? This is equal to 5.16 milliampere. So you got the value of IE. Now you can find VCE. What is VCE? It is VCC minus IC into RC plus RE. So this is nothing but 10 minus IC is 5.16 milliampere into RC plus RE. And what is RC? RC is 1 kilo. So 1 kilo plus 560 ohms. So you will be getting VCE as 1.95 volt. So you got VCE and you got IC and you got VCE. Now you can draw the characteristics curve and draw the load line and mark the Q point, right? Now I am going to draw the characteristics curve first. This is the characteristic curve for the transistor. Okay, now we can see how to draw the load line. Okay, so we have to find the x-intercept and the y-intercept. This is the load line. So what will be this point? How much? And what will be this point? So this is nothing but VCC that we have discussed in the previous slides, like we have discussed in the previous slide, right? Yes, you can see here it is VCC and this is VCC over RC plus RE. So I am going to discuss this VCC. How much VCC? It is 10 volt, and this is nothing but VCC over RC plus RE, that is 10 divided by RC is 1 kilo plus 560 ohm. So you can calculate this value. So that is the IC set, we can say, that is the maximum current you can get for this circuit, IC set. Now I am going to mark the Q point, and you know this is x-axis is VCE and y-axis is IC, as we have explained before. Now I am going to mark the Q point. The Q point is you can see we have a VCE. VCE is 1.95. Maybe this is 10 volt. So this is 5, maybe 2.5, this is maybe 1.95 here. It is 1.95 volt, and this current is corresponding current is 5.6 milliampere. So this is the Q point. That means 1.95 volt and 5.6 milliampere. So this is how you can mark the Q point. This is the Q point, or the quiescent operating point. So this is how to solve the problem with the load line. Okay, now what is the speciality of this circuit? You can see that how we can explain the stability of the circuit. The stability of the circuit can be how about the stability of this? The circuit is stable actually. So we will explain the stability of this circuit. Okay. First of all, we will be making a qualitative analysis, and we will illustrate that the circuit is stable by using a problem. Anyway, this is RE, this is R1, and this is R2. Now the transistor is having a beta DC. Okay, now let us assume that the transistor was having a beta DC initially, and due to the temperature, due to the variation in the temperature, suppose the temperature changes, what will happen to beta DC? The beta DC also will change. Since this we are giving the VB as fixed, VB will not be changing anyway. You can see that due to this is IB, IB will be fixed. For example, IB, there will be a particular IB flowing into the base of the transistor. As the beta DC changes, what will happen? You can see there is a resistance at the base or at the emitter. This is known as emitter resistance. Emitter resistance. Now, since beta DC changes, what will happen? The IC changes, right? Since IC changes, IE also changes. Let us assume that we increase the temperature. Okay, suppose temperature has been increased, then what will happen to beta DC? Usually beta DC also will increase. Because of this increase in beta DC, you know that the IB is fixed, so what will happen to IC? IC will be also increasing. As IC increases, you know that IE also will increase. But you know the voltage across RE is nothing but plus minus, it is nothing but IE RE. So what will happen? The voltage IE RE, this also will increase because of the increase in IE. What is this IE RE? It is nothing but VE. Since the VE increases, so you can see that VE also will increase. Since VE increases, what will happen? You can see like this. You have a fixed VB and you have a transistor like this. This is 0.7 and this is VE. As the voltage VE increases and the VB is not changing, this is fixed, you can see that the current IB will now try to reduce. So the IB will now try to reduce, which will result in reduction in IC. That means whenever there is a change in beta DC, immediately the voltage across RE will increase, and this will lead to decrease in IB. Why it is decreasing? You can see that if this voltage across VE increases, this is VE increases, then the current which is coming from this side, from VB, will be reducing because the voltage at the other end is high, right? So this will lead to decrease in IB and it will lead to decrease in IC. So whenever there is a change in IC due to the beta, immediately it will come to the same point, okay, almost to the same point. So we can explain it in a good way. Let us assume that we have a temperature variation. Temperature increases, what will happen? What it will leads to beta DC, increase in the beta DC, and this will lead to increase in IC. However, this will leads to increase in VE, and this will lead to decrease in IB, right? This will lead to decrease in IB, and finally it will lead to the decrease in IC. You understood? So this is what happening. So you can see, I will explain this. It will leads to decrease in IC will be decreasing, okay, it will leads to decrease in IC. So you can see that it will leads to decrease in IC, so that the IC become stable, okay. So whenever IC becomes stable, automatically it will leads to the stability in VCE also, okay. We can see VCE is here, the voltage between the collector and the emitter. So this is regarding the qualitative analysis regarding the stability of the voltage divider bias, okay.